So let's continue our discussion of the groups of units, mod M. So now we want to address a general modulus. So we've established that for any odd prime power, the group of units is always a cyclic group, and that for the prime 2, it's a cyclic group only for 2 and 4, and then as soon as the exponent is 3 or greater, it's a direct product of a cyclic group of order 2 and a cyclic group of order 2 to the e minus 2. So in this section, we first of all want to express Gm as a direct product of cyclic groups for any value of m. And then we want to ask, well, for what m is this going to be a cyclic group in the end? So we need to ask, when is a direct product of finite groups a cyclic group? And in particular, we want to determine all values of m such that Gm is a cyclic group, which would mean that m would have a primitive root. And there's a great advantage in number theory for moduli that have primitive roots. Take the primitive root 2. Then you can say that every integer is a power of that fixed value. So we've seen that as a consequence of the Chinese remainder theorem, that if we write m as 2 to the e times a product of odd prime powers, that the group of units mod m is isomorphic to the group of units mod 2 to the e, right here, across the group of units mod p1 to the e1 times ... all the way down to the group of units mod pk to the ek. So if the exponent e is 1 or 2, so that the first component here is a cyclic group, then we already have Gm as a direct product of cyclic groups by the fact we established last time that for any of these odd powers, g pi to the ei is in fact a cyclic group. For e greater than or equal to 3, we have to go one step further and express the 2 component right here as a direct product of a cyclic group of order 2 and a cyclic group of order 2 to the e minus 2. And that gives us Gm as a direct product of cyclic groups. So now we want to ask, well, when is this direct product itself another cyclic group? Okay, first we'll do an example. Let's express the group of units mod 7000 as a direct product of cyclic groups. So I factor 7000. So 7 times 1000, and 1000 is 10 cubed. So 2 cubed times 5 cubed. So the group of units is isomorphic to the group of units mod 2 cubed cross the group of units mod 5 cubed cross the group of units mod 7. And for the power of 2, it's 3. So this would be a cyclic group of order 2 crossed with a cyclic group of order 2. Right? There are 4 units. This is the negative 1, and this would be the group generated by 5. The group of units mod 5 cubed, okay, so the order is the Euler phi function, so phi of 5 cubed is 5 cubed minus 5 squared, which is 100, and it's a cyclic group, so this would be a cyclic group of order 100. And the group of units here, the Euler phi function of 7 is just 6, so that's a cyclic group of order 6. Okay, so we've expressed G7000 as a direct product of cyclic groups. Is this direct product a cyclic group? So how do we address that question? You got a group of order 2, group of order 2, group of order 100, and group of order 6. Well, I claim that this is not going to be a cyclic group. And the problem we have is that these numbers right here are not relatively prime to one another. So let's see what's going to go on. So we'll address that question. How do we tell, when I'm taking a Cartesian product of cyclic groups of this type, whether the outcome is a cyclic group? So not relatively prime. So this is not cyclic. In fact, you probably remember this fact in group theory that the Klein 4 group is just C2 cross C2, and every element has order 1 or 2. There is no element of order 4. So this is a non-cyclic group. And that's what's going on in this example, why it's not a cyclic group. Okay, so to address the question, let's first of all look at a lemma on least common multiples. So for any integers mi, I claim that the least common multiple of m1 through mk is at most the product of the moduli, with equality if and only if the moduli are pairwise relatively prime. So it's the second part here that's really the significance. This is a trivial inequality. Why is that? Well, the product of the moduli is clearly a common multiple, and this is the least common multiple, so it's smaller than any other common multiple. Okay, so that's just definition. Okay, proof. So let's use the trick of representing all of the moduli using the same prime powers. So let's say m sub I has a prime power factorization where j goes from 1 up to, say, L of pj. So we're going to have the same primes, but we'll have different exponents. So I'm going to have to put a double subscript here, e sub ij, for some distinct primes p1, p2 through pl, and e sub ij greater than or equal to 0, where I is going to go from 1 to k. That's accounting for the k different m sub I, and j is going to go from 1 to L. Okay, so these mi have prime power factorizations where I'm using the same primes. Then, if I want to calculate the least common multiple, what's that going to equal? Well, this is the formula we've seen, where you just take the biggest exponent. So you're going to take the maximum, where I is going from 1 to k, of e I j. So for each prime pj, you take the maximum exponent over all the different moduli. And so, when is this going to equal the product? So the product how does that compare? There you have to take the sum of the EIJs. Okay, let's put this together on the next slide. So thus, the least common multiple is the product if and only if, when you look at the maximum, where I goes from 1 to k of e, I, j, this should equal the sum, I going from 1 to k of e, I, j, for each of the primes. So each j going from 1 to L. So the maximum is the power we get for the least common multiple. The sum is the exponent we get for the product. Well, when is a maximum of a collection of numbers equal to the sum of the numbers? That can only happen if exactly one of these numbers is positive. So for each j equaling 1 to L, exactly one of the e sub ij is greater than 0, and all others equal 0. Right? If two of them were positive numbers, then certainly the sum would be bigger than the maximum of all those values. So, well, what does that mean? Well, that just means that the p sub i's can only divide, I mean, for each pj, each prime divisor, pj, there is only one moduli that contains pj as a factor. Only one modulus m sub I with pj dividing m sub I. And that means the m sub I share no common prime powers. I mean, they're pairwise relatively prime. So mi, we got too many i's, j's, let's just write it in words. The m sub I are pairwise relatively prime. QED. Again, we'll need one further lemma on orders of elements. So suppose that Gi is a group, I going from 1 to k, that Xi is an element in Gi of a finite order. So X is a k-tuple of elements in this Cartesian product. Then I claim the order of this k-tuple is the least common multiple of the orders of the individual components. So let's see what's going on there. The order of the k-tuple. Okay, so I need to find what's the smallest power such that x to that power is the identity. So if I let ei be the identity element in Gi, then E1, E2 through EK is the identity in the Cartesian product. So we need to find the order of x. So x, I don't have an n yet, to the n equals this identity element right here, would be equivalent to saying what? Well, x itself is this k-tuple, and multiplication is component-wise. So that's equivalent to saying this. Is E1 through EK. And that's equivalent to saying that xi to the n equals EI. And that relationship is taking place in the group G sub I. So I'm just matching the ith components of these tuples here. And we've seen, well, you're in a group, so that means that the order of xi is a divisor of n. Order of xi in the group Gi is a divisor of n. All right, so x to the n is the identity if and only if the order of xi is a divisor of n for all values of I. Aha, that just means that n is a common multiple of all of these orders. Order of the xi's. Okay, now look what we've just written down. I've said that x to the n is the identity if and only if n is a common multiple. Now to get the order of x, we want the smallest value of n satisfying this identity right here. And therefore we want the smallest value of n that's a common multiple. Well, that is the least common multiple, QED. So, when is a direct product of finite groups a cyclic group? So let G1 through GK be finite groups. I claim that the direct product is cyclic if and only if each of the groups itself is a cyclic group and the orders are pairwise relatively prime. Proof. So G1 cross GK is cyclic. What does that mean? If and only if there is some element that generates this group. So if and only if there exists some x equal to x1 through xk in this Cartesian product, with the order of x equal to the order of the entire group. Well, what does that mean? Well, that's equivalent to saying the order of x is this k tuple, and what's the order of a Cartesian product? That's just the product of the group orders. And the lemma we just saw said the order of the k tuple is the least common multiple. So we're coming up with some equivalent statements. This is the least common multiple of the order of x1 through the order of xk, and that should equal this product here. Okay, now, what do we know? We know that the order of xi is always going to be a divisor of gi. Xi is an element of this finite group. So the order of xi in particular is less than or equal to the order of gi. So let's put this together as a string of inequalities. Thus, this product of these cardinalities equals this least common multiple and we said the least common multiple of a collection of positive integers is less than or equal to the product of those values with equality here. Let's highlight that in red. With equality when? If and only if these orders are pairwise relatively prime. So the order of xi, xj equals 1 for all I not equal to j. And this is then less than or equal, since each one is smaller than the order of gi, product I goes from 1 to k of the order of gi. And when do we have equality here? With equality, if and only if the order of xi equals the cardinality of gi. So look at what we've established. On the left-hand side, I have the product of the group orders, and on the right-hand side, I have exactly the same value. Therefore, we must have equality throughout this entire equation right here, which means we must have both of these conditions right here and right here being satisfied. So in summary, the Cartesian product is cyclic if and only if there exists some x such that we do have equality in the start equation, and that is equivalent to having both of these conditions being satisfied, that the cardinalities of the orders are pairwise relatively prime, and that the order of xi is the cardinality of gi. But what does that last statement say? Saying that the cardinality, or the order of xi is the cardinality of gi, is equivalent to saying that xi is a generator. This is true for all of these values, which means that gi is a cyclic group. Thus, the Cartesian product is cyclic if and only if there exists these xi's in the gi's, with gi being generated by the xi's and the orders are pairwise relatively prime. That is, the orders of the groups, right? These are now cyclic groups, and the order of the group is the same as the order of the element. So the order of gi and gj is 1. The greatest common divisor is equal to 1. QED. Exactly what we wanted to prove. So now we can finally turn to the group of units mod M, with M being general, and ask, for what M is this a cyclic group? So I claim the following: let M be any natural number, Gm is cyclic if and only if M is 1, 2, 4, an odd prime power or 2 times an odd prime power, where this f is some positive integer. And the proof is, we've done all the hard work now. So we've seen that if m is 2 to the e, p1 to the e1, pk to the ek, for some odd primes, p sub I, gm is isomorphic to g2 to the e cross g p1 to the e1 cross g pk to the ek. And so by the theorem we just proved, this Cartesian product of finite groups is cyclic if and only if 2 conditions hold. Each of the groups is cyclic, and the group orders are pairwise relatively prime. The group orders are pairwise relatively prime. This first condition here is immediately telling me that E has to be 0, 1, or 2. And what do we know about odd prime powers? Now, for any odd prime p sub I, what is the group order? The cardinality of g pi to the ei is the Euler phi function, which is pi to the ei minus 1 times pi minus 1. And that's an even number, because this term right here is even. Which means you can have at most one odd prime factor if the orders are going to be pairwise relatively prime, because any 2 would have a common factor of 2. Thus, there exists at most one odd prime divisor. So then, we have different cases. Case 1, E equals 0, and the modulus would then be a single prime factor, so P1 to the E1. Case 2, E equals 1, so that means you'd have a 2, and then a single, at most a single prime factor, like that. And case 3, let's try this out. If E equals 2, and we had a prime factor, would that be a legitimate cyclic group? So in cases 1 and 2, we know that these are cyclic groups. No problem there. In case 3, what if we have a 2 squared times your single odd prime factor? Well, if E1 was strictly positive, then what is the GCD of 2 squared not 2 squared, but phi of 2 squared, and phi of p1 to the e1. So we're looking at the groups of units of these two components. Well, phi of 2 squared is 2. And this is an even number. So this does not equal 1. And so we would violate the pairwise relatively prime condition. So the only time we can be in case 3 is when E1 itself is 0. So for case 3, if E equals 2, then M must just equal 2 squared. And thus we have identified all of the cases of the theorem. So look again at the theorem. It's cyclic if and only if M is 1, 2, 4 in odd prime power or 2 times in odd prime power.